I think I'm going to use the
Okay, I think we'll get started. So it's my pleasure to introduce Mario, who will tell us about collages of string diagrams.
Thank you. And thank you so much for everyone organizing. I can imagine it's a lot of work. Okay, so can you hear me? Yeah. Okay, so I'm going to be presenting joint work with Dylan Brightwhite. So if you see him, you can ask him. I think he's also going to be on the question time. So it's entitled Collages of String Diagrams. And we are going to be giving semantics or explaining what happens when you mix string diagrams from different monoidal categories. So I'm going to start by saying that you know string diagrams for monoidal categories. We use them to talk about processes, to describe processes. And you have seen many of those during these weeks. You will see many, so I'm not going to stop on this idea. But the idea is that you're going to have resources and processes, and you will use the syntax of string diagrams to talk about them. And we have good theorems to show that this is somewhat complete for monoidal categories. Same happens with bi-categories, even if these are less well-known. You use the same string diagrams, but now you color the regions. And these are useful to do things like formal category theory. You can prove properties of adjoints using string diagrams for bi-categories. The same thing holds. You have still some incompleteness for these diagrams. But then, so this is what we know how to do, monoidal categories. We know how to do bi-categories. And then when we do applied category theory, we do something completely different. So these are examples of many string diagrams that you will find in the literature in many different forms, and that may resemble bi-categorical diagrams, even if they are about monoidal categories. So for instance, you have here incomplete diagrams at the beginning. These appear in working in quantum, in resource theories in the paper by Keck and others. They appear in open games, they appear in optics, they appear in causality. The second one is functor boxes, which you may know, that give you a way of talking about monoidal functors in monoidal categories. So lax monoidal, or plax monoidal, strong monoidal. The third one is internal diagrams that let you away. So they are using in categorical topological quantum field theory. I know also there is a paper by Lovsky and Sanasi where they use that for explainable string diagrams, where you can go inside a string diagram and explain it in terms of a different category. Then you have string diagrams for pre-monoidal categories. This comes from a paper in the 90s by Alan Jeffrey that was studying how to do imperative programming in string diagrams. And then the string diagrams that motivate this paper, this collaboration, is that I saw that Dylan was using these string diagrams for bimodular categories and for optics. And these diagrams have multiple regions representing how some monoidal categories act on others. All of this is to say, even if we have anti-string diagrams for bi-categories, the fact is that you will find in the literature many string diagrams that are not, strictly speaking, string diagrams for bi-categories. So we are going to capture this, and we are going to start by the last ones. The last ones are bimodular categories. So first I need to tell you what is a bimodular category. A bimodular category is going to be to a monoidal category what a bimodule is to a monoid. So if you have that, you can categorify a monoid, and then the set becomes a category, and then the multiplication becomes a functor, and the qualities become natural isomorphisms. You can do the same with a bimodule. You have a set and two monoids acting. So that means that you are going to have a category, two monoidal categories acting on it, and now the qualities that you could impose become natural isomorphisms. you need to impose later some coherence conditions that work very similarly to the ones in monoidal categories. So you have some pentagon and triangle equations, and you have a coherence theorem that works similar to the one of monoidal categories. Okay, so why do we care about these bimodular categories already? So I'm going to argue that when you are doing theories that are very simple, you already find the need to use this kind of thing. Let's imagine that we want to model a theory of an algebraic theory of what it means to share some state. So this is something that happens out in computer science where you want to share some resource and there will be two parties accessing it, like writing and reading. So let's present an algebraic theory in the same way that we present an algebraic theory for bimodules or Frobenius monoids. The only difference is that we will have two regions for the two parties, but we are going to impose equations in the same way we would do in algebraic theory for monoidal categories. So for instance, we say that if two parties write, the second thing you write is the one that is preserved, and the first one that you write has been overwritten by the second one. So you just discard what happened there. So these are the equations governing this overwriting. And then you will impose some equations that explain how some things like getting and putting work. These, I think, are simple. It's just to say, if you get some resource and you get it again, well, that's the same as getting it once and copying it. So now you have, with all of these equations, you have an algebraic theory of what happens when two parties share a resource. Trying now to justify that a theory like this can capture interesting things. In fact, if one of the features of these shared state theories is that you will have race conditions, you can write these race conditions in terms of the string diagrams. So imagine you have two parties that need to increment a counter. There is this classical notion in computer science that if you say A is going to increment 1, B is going to increment 1, if I run both, they will increment 2, right? 1 and 1. But if they interleave the actions, so one reads from a register and then increments, the other reads meanwhile and then increments, it may happen that they just increment once. Okay. And can we solve the problem? So if there is a solution in computer science already that is done by logs, you can do the same thing on an algebraic theorem on bimodular categories. You just put logs, and then the race conditions are going to be typed. Those that cannot be typed would be the race conditions. So someone is trying to write or read, but someone else has read first. So they mark the resource as locked, and then you cannot access it until someone writes on top of it. So why I'm saying all of this story is to tell you that bimodular categories allow us to do some algebraic theories that are interesting. So we have a very naive theory of something like concurrency, something like a shared state, not full concurrency, but a shared state. But they have diagrams that are different from the ones of monoidal categories, and we want to capture those.
Yep.
Probably. Where? Right, that should be triangle. And the other below should be triangle. Yes, thank you. Yeah. Assuming nothing but the structure, assuming. And the equational theorem I'm talking about here. So with all these equations on top of the equations of right. I'm asking these equations on top of a bimodular category, right? So my point is, you have bimodular categories and you can do algebraic theories on top of that in the same way that we do Frobenius on top of a monoidal category. Right. This is an algebra that you may think, and I'm trying to argue that these are already expressive enough that you can start doing things like this, right? Yeah. But of course, it's not the only thing one could do there. Right, so you can show now that these string diagrams for bimodular categories are going to be sound and complete. And how do we prove that? It's by taking very seriously the idea that we can use the string diagrams for bicategories, and these are like surface diagrams. These are like diagrams with regions. So we are going to use that we know soundness and completeness for diagrams of a bicategory, and we are going to transfer that to the string diagrams for bimodular categories. So I think.
We had a question if it is active.
Yeah, thank you. So I think Cole was asking if bimodulars are categories. Yes. So yes. So I think you will find this called bicategories. But I think the name is a bit confusing because later we're going to be talking about bicategories and biact-categories, and I think it will get confusing very quickly. So I'm calling these bimodular categories. I argue that if monoidal categories are two monoids, these are two bimodules. Yeah, thank you, Cole. Okay, so string diagrams or bimodular categories are one thing, but I am promising you that we are going to do this in much greater generality. So we have seen that we can glue together two string diagrams from different monoidal categories and get bimodular categories, but something like that is happening when we do functor boxes. For instance, we have string diagrams for two different categories, and we are using the same in the same string diagram. Or when we do incomplete string diagrams, so these comps that you can see in the literature in quantum are incomplete diagrams that can use parts of different string diagrams for different monoidal categories. Or premonoidal categories, where everything is on the same category, except for a single wire, that is the red wire, that is not part of the monoidal category, and you cannot tensor it together with itself. So in many cases, you are finding string diagrams for different categories, and they are all put together. So the idea that we are going to use here is that all of these things are going to be string diagrams. Functor boxes are going to be string diagrams. Incomplete diagrams are going to be string diagrams. We are going to take them very seriously and try to make them into diagrams in a suitable by category. Okay. So any questions until here? So let's now take functor boxes seriously. We put them usually as something that you construct on top of a string diagram. So you will have a string diagram, and then you have boxes that are operators on top of them. But what if we just take them to be also strings, right? We have string diagrams for bicategories, so we already know how string diagrams for multiple regions need to work. And then we can have wires that translate from the inside to the outside of a functor box. So let's do, in the same way that we were doing first the theory of shared state, in the same way that we do the theory of bimonoids, let's do just a theory of functor boxes. So we are going to pick some generators for the morphisms of the category outside the category, some generators for the morphisms inside the category. We are going to have some morphisms that say how the shape of the functor box is going to work. Here I'm doing lax functor boxes, for instance. So you will have that the box can start from the monoidal units, and that you can glue together two boxes. If you would have op-lax, then you would just change the direction of things. If you would have a strong, then you would have both, and they would be inverse to each other. So we asked for these generators on a bicategory, and then we are going to write the theory of functor boxes relative to a bicategory. So we are going to take seriously the idea that functor boxes are also string diagrams. So when you do that, you can prove, again, relative to the soundness and completeness for bicategories, that string diagrams for functor boxes are going to be also sound and complete. I'm working all the time here with the strict case. So we are going to have strict monoidal functors, lax or op-lax. We are going to have the two categories instead of bicategories, but the same thing works mostly how it would work for monoidal categories, right? But later you have that any non-strict is equivalent to one that is. Okay. Can we repeat this technique elsewhere? So we can do something like that now for incomplete string diagrams, so these comb diagrams. Let's take them seriously as they are really just string diagrams. It is not like we have parts of string diagrams around, but we really have that this split into boundaries that separate what is the inside of the box from the outside of the box. So we take the same technique, and we can give an algebraic theory of incomplete diagrams in terms of a bicategory again. And we have generators for objects, generators for morphisms, a structure for how these boxes with incomplete diagrams need to work. And the only problem here is that you may want a bit more than that. Because usually when we work with incomplete diagrams, we are going to be doing reductions of them. So for instance, if I have a diagram that ends in an object A and a diagram that starts from an object A, I may want to glue both of them. And for that, I need a reduction. So the problem here is I was already using bicategories, and I'm asking now for a new dimension so that I can do reduction. So this is giving us 3 categories, right? So this would be tri-categories or 3 categories in the strict case. Right, so you could do this. You could have a theory of incomplete string diagrams in terms of tri-categories to have a syntax. You will have some generators for your category. You will have some generators that manage how the shapes of the diagrams may work. You will have, for any object, you will have the opportunity to end the string diagram on that object. You will have then reductions that allow you to glue diagrams together to generate identities. You will have reductions of the shapes and so on. The problem here is that all of this is needs for us to have a theory of tri-categories. So here is when we need to say this is a conjecture, because if I want to use tri-categories, I would like to have some justification for the string diagram calculus that I want to use, right? So if I do tri-categories, I'm doing a string diagram calculus where I do bi-categories, and then I put reductions of bi-categories. And there is some work on this for monoidal bi-categories, which are not yet tri-categories, but I haven't seen at least work that allows me to say confidently, yes, these are the string diagrams for tri-categories and you can use them. Okay, so here is when this opens a way, if someone wants and someone does it, I would be very happy. That is to try to prove that you have some coherence theorem for tri-categories, that I can use the same string diagrams that you use for monoidal bi-categories, and that all of this is going to work nicely for tri-categories. This is not what we will do in the paper, but we assume that as a conjecture. So it seems that something like this should be true, and then we assume it as a conjecture, also justifying ourselves that the case for monoidal bi-categories, so the same thing but without regions, has been already studied, and there is some strictification theorem. But even with that, we are missing results before we can say that we do tri-categories. Okay, so I have been giving many examples of many theories that you can do. You can do the theory, the algebraic theory of incomplete diagrams. Before we were seeing the algebraic theory of functor boxes. I'm going to try to give now compositional semantics for all of them. So where are all these diagrams living? The diagrams for coms, the diagrams for incomplete diagrams, the diagrams for functor boxes. Can I have a single category where the regions are monoidal categories and I can do all these collages of string diagrams just in that single category? This is what I'm going to try to answer now. So let's construct one category that is going to be a tri-category necessarily, where we can do all these reductions and all these diagrams and give meaning to all of them, okay? So any questions until now? Okay, so the tri-category that we are going to use is that of pointed bimodular profunctors, which is a very long word with many things. So I'm going to explain that very slowly and try to argue that even if this sounds like very technical, it's something natural that you may think if you are trying to do something like this. So why do we want pointed bimodular profunctors? So this is the whole data simplified of what we would like for that tri-category. I'm going to go through the dimensions one by one, and let's try to see how they correspond to the things we are doing. So the first thing that we want is that our regions are monoidal categories, right? This is what I was saying from the beginning. I want to put together many monoidal categories and make them, all of them, interplay in a single string diagrammatic calculus. So the regions are monoidal categories. Let's take them as regions. And if we have the empty region, so something where nothing is there, well, that is going to be just a terminal monoidal category, just a category with one object. So 0 cells are monoidal categories for the tri-category we are building. Now, what are the 1 cells? So 1 cells need to contain inside objects of the monoidal categories, right? Because I want still to be able to do string diagrams for those monoidal categories inside. But also they will need to have some objects for the bimodular categories that are in between the monoidal categories, right? So we are going to pick, for every wire, we say that is an object on some category. So every wire is going to be a pair, a tuple, that contains a category and the object we picked inside that category. And that category needs to be bimodular with the 2 regions that has to the left and to the right. So that is going to be a bimodular category, and then it has 2 regions, 2 monoidal categories that act on it on the left and on the right. Right, so now wires, 1 cells are going to be pointed bimodular categories. And it's not so bad, it's what we wanted, right? So bimodular category and 1 point that we pick inside there. Now we need to compose them, so tensor them. But we already have a tensor of bimodular categories. So answering the question that called, okay. Putting down. Sorry, because here the screen stops working. How does it? How should I make it working? Does anyone know how this works? Projector 1 and 2, perhaps? So perhaps it's like 1, 2, 3, 4. Yeah. That one, yeah.
Oh, yeah. When the guys responded, cool.
Okay, thank you. Sorry. Okay. So we can still tensor by modular categories if we want even. Oh, I think that's. Thank you. To know for the next the week. Okay, so I was saying that it's not too bad to tensor by modular categories because you will have you already have an operation that has been well studied that is a tensor of bimodular categories. If you know the tensor of bimodules, it works the same, but now categorified. I think Cole was asking before if this has something to do with categories. So I think you will find a description of all of this story in the work of Capucci and Gavranovic, where they call them bicategories. And then you have the tensor of bicategories. Okay, so this is all to say we have 0 cells, monoidal categories. 1 cells are pointed by modular categories. We know how to tensor them. What are 2 cells? Well, we need to pick now, before we were picking an object inside a category. Now we need to pick some family of things that can go in between and pick one of them, one of these morphisms. These are going to be usually home sets of the categories that we are using. So if we have a monoidal category, we want to be able to pick a morphism of the monoidal category. And then we may be able to compose them on top and on the bottom, and that is to say that we have profunctors. So the profunctor part is just about saying that we may be able to pick one morphism from the monoidal categories. Because we are not only saying that we have a profunctor, we are picking one element on that, we have pointed profunctors. And also because we want them to interplay nicely with the rest of the structure, we need to let them be tensored on the left and on the right by 2 objects of the category. So these are going to be bimodular profunctors. So in the same way that monoidal functors are the nice notion of functor between monoidal categories, bimodular profunctors are going to be a good notion of profunctor between bimodular categories. Okay, so I can go back to the scary slide. Now I'm saying that we have 2 cells that are going to be pointed by modular profunctors. So these are going to be profunctors with a point and some compatible transformations that let me tensor on the two sides. These are also called Tambara modules. And I think they also appear in fusion categories and other settings with different names. I'm going to call them bimodular profunctors just to keep the names nicely. And then the 3 cells are going to be just the homomorphisms of these bimodular profunctors. So these are going to be natural transformations preserving these actions. And they need to additionally preserve the point that we are asking. So with all of this, now you can imagine how we can compose all the different monoidal categories into a single string diagrammatic framework, where we will have objects from different monoidal categories and points that belong to different monoidal categories. So for instance, if we want to do compositional semantics or functor boxes, now we can pick all of the pieces of the functor boxes and pick one profunctor for them and one point inside that profunctor. When we compose them, we compose the profunctors and the points that they have inside. When we tensor the profunctors using that they are bimodular profunctors, and so on. Same will happen for incomplete diagrams, even for the reductions. This is still a tri-category, so we can do the reductions. And I think with this, I'm almost done. Okay, so all of this is to say, now we have some tri-category where we can try to give semantics to all these diagrams. We have like a very big tri-category where every time you draw a string diagram of monoidal categories, you can always try to embed it there. And you can even speak about pieces of one diagram and put multiple monoidal diagrams inside of the same category. So there are two directions that one can go after this. One is try to make this tri-category true. I was saying before that there are many things that we need to assume about conjectures, as conjectures. But it's even worse, because I was saying that we have 3 dimensions, and actually this is a monoidal tri-category as well. You could put many, you could tensor together string diagrams, and that works. And you even have like a compact structure where you take the reverse monoidal category. So the monoidal category with tensoring A with B is B with A. Of course, who is going to try to do this? Because it's a monoidal tri-category, it's a compact tri-category, you would need to study the theory of 4 categories, I guess. So I'm not going to try to go that direction. So I'm going to give you the alternative direction here that I think is more adequate to the conference. That is, well, let's do then some applications. So I have been talking about something a bit theoretical, right? Why do you want semantics of a very complicated category where you can put all the monoidal diagrams inside, right? What's the point of all of this? So I think perhaps what I can try to argue now is that if you're going to implement string diagrams for monoidal categories, and mind you, not only for symmetric monoidal categories, that are sometimes easier because then you don't care about the swaps and all of that, but for monoidal categories, then usually it's not too difficult to also implement by categories. Because you're going to implement string diagrams for monoidal categories and you're going to be taking care of the regions between them. So it's usually not too difficult to go that way. But once you do that, you are not only getting monoidal categories, you're getting a lot of other things that we like when we do monoidal categories. So you may be not very convinced of implementing by categories because you say, well, why do I care about an extra dimension, right? I just want to do my string diagrams for monoidal categories, but that is going to help you do things like functor boxes, pre-monoidal categories, bimodular category, internal diagrams, many other things, many other nice things that people use anyway when they do string diagrams. So this is to say, if you're going to implement monoidal diagrams or monoidal categories, you can try to do the second step, do by categories, and then when someone asks you, do you have functor boxes? You say, yes, of course, because we have a sound and complete calculus depending on by categories. So to prove my point, I took Homotopy.io. So Homotopy.io has an implementation of by categories, right? So let's try to take this very seriously. Homotopy.io is not like they have functor boxes explicitly, but I can still try to encode the functor box with the theory that I have that is relative to a by category. So I can just take that diagram very seriously and go to Homotopy.io and reason with that. And if I put the corresponding 3 cells and everything, the corresponding equalities, I will have a sound and complete theory for functor boxes. So yeah, I think that's all. Thank you very much.
Thanks, Mario. Any questions in the audience?
I have a question on the internet.
We'll just take one in the room and then we'll take the question online.
So what was the connection between the 3 cells in your tri-category and string diagrams in general? Something about these gaps and...
So this appears when you try to do, so I may repeat the question, what are the connections between the 3 cells and the string diagrams in general, right? So the thing I'm trying to model there is when you do something that is called incomplete string diagrams or internal diagrams. And in this case, what you will have is that you may want to glue multiple diagrams for different categories. So the 3 cells are allowing you to have them separated and then glue them. So this operation of gluing becomes also part of this, sorry. Right.
Thanks.
Thank you.
Cole, I think you had a question online.
Oh yeah. Regarding your, thanks for the talk. This is nice, really nice by the way. But regarding your this comment that this subsumes like string diagrams for monoidal categories, how do you get around like the problems that say in like pointed profunctors or pointed time bar modules, it has weak interchange, and there's like all of this extra coherence data?
Right. So right. So when you do diagrams for profunctors, so I'm going to basically repeat your question. I don't think I have a good solution for that. You may want to have a I think you may have a good solution for that, but I'm going to repeat your question. So there is a problem with this, that is that I'm using string diagrams for, I'm saying that I'm going to assume when I assume the conjecture, sorry, I have to go back. When I assume the conjecture, I say, let's assume that this works like Bartlett's wiring diagrams for monoidal by categories. When you use these ones, you need to be careful because the interchange is not going to be strictly working, right? Like it's not, you cannot do interchange on the nose. You need to have some isomorphism that allows you to do interchange. And this is important because in profunctors, they are going to be symmetric. So if you swap two profunctors, that's not the same as leaving them in the same place. So there is a reason why you cannot strictify that. So there is, you don't have interchange in the wiring diagrams or monoidal by categories, and I cannot assume that you will have interchange in the string diagrams for tri-categories. So I'm not claiming I know how to solve that. I think Cole is also pointing to the fact that when you do bimodular profunctors, there might be another way to getting around that problem, but I am not solving it. Does that answer the question, Cole?
Yeah, thank you. I'm just curious because it seems like very nuanced, like stuff's going on behind the scenes.
Okay.
Thanks for
Thank you.
answering.
Are there any other questions? Yes.
This is probably naive, but the word collage of a profunctor means something, and it's in your talk title. Do those two meanings come together?
Here I'm taking collages not in the same direction as they're usually taken, because you would take them in the direction where you compose two profunctors together. So you take a collage and that's a category. I'm taking them in the direction where I put two bimodular profunctors tensored, right? So these are collages in a different direction and are not the same collages that people usually call collages of profunctors. But I'm taking the term because this comes back to a paper by Street where he says something like that Bob Walters was using the term to call anything that was some kind of lax colimit under the intuition that was something like a collage of things, like putting together multiple things, right? Sorry? So this is the part that I think Dylan should answer better than me. When you're putting multiple monoidal categories together, so for instance, when you do the by categories, the bimodular categories, right? You are going to be getting that as a lax colimit in the by category that has the two monoidal categories between them, and the edges from one to the other are the objects of the bimodular category. So I cannot answer many technical questions here, but if Dylan is in the audience, perhaps he wants to say more. I think there is a sense in which you can show that essentially it's the same idea as collages, but I haven't worked on that too much. Thank you.
Okay, I think we might stop there. Let's thank our speaker again.